that I welcome all of you to this next session of the climate change seminar series. And our speaker today is very well credentialed, as you will hear in a few moments. She's also a friend, and we work together on various aspects. And so it's a personal pleasure to welcome Dr. Krieger here for us. We're focusing on air quality and carbon emissions and so forth. And as everybody probably knows, climate change can impact air quality, and conversely, air quality can impact climate change. Air pollution not only contributes to climate change, but it also can exacerbate it. Now, the most prevalent types of air pollution are smog and soot. Probably we all are very familiar with smog and soot. Smog occurs when emissions from combusting fossil fuels react with sunlight. And city dwellers, most of us are city dwellers, are very familiar with smog, especially during temperature inversions. Soot, or particulate matter, is made up of tiny particles of chemicals, of soil, smoke, dust, allergens, can be in the form of gas or solids, and they are carried in the air. And the tiniest airborne particles in soot, whether in the form of gas or solids, are especially dangerous because they can aggravate respiratory illnesses such as COPD and asthma. And these toxic particles can be lodged deep into the lungs, thus causing breathing issues and damaging the lungs. Climate change also increases the production of allergenic air pollutants, including mold, and that's thanks to damp conditions caused by extreme weather and increased flooding. We had a talk about water resources last week, and also pollen. And there are many hazardous air pollutants that can and do harm, including polycyclic aromatic hydrocarbons, or PAH, particulate matter, particularly PM 2.5, and ozone, especially ground level ozone. And all of these, plus more, have implications for human health. So that being said, much of the discussion about air pollution and climate change focuses on carbon dioxide and methane. Carbon dioxide, of course, comes from combusting fossil fuels, and methane comes from natural and industrial sources, including large amounts that are released during oil and gas drilling. Working to reduce the world's carbon footprint is deemed essential for Earth's survival. And that is what I mean by carbon footprint. It's the total amount of greenhouse gases, including carbon dioxide and methane, that are generated by human-created actions. So today's speaker is going to focus on these issues and do so in much more detail. Dr. Elena Krieger is a director of research at PSE Healthy Energy, where she oversees the organization's scientific research efforts. Her research focuses on renewable energy resources, energy storage, air quality, and environmental justice issues. In particular, she has characterized operational emissions, health, air quality, and environmental justice measures for power plants. I had to read that, Elena. For power plants across the country, and develop pathways to mitigate power sector impacts through the integration of clean energy resources. She received her BA in physics and astronomy and astrophysics from Harvard University, and a PhD from the Department of Mechanical and Aerospace Engineering from Princeton. And as an aside, as I mentioned to her yesterday on our phone call, we have our colleagues in Brazil joining us on this Zoom. And Brazilians will be interested to know perhaps that Dr. Krieger actually lived in Brazil for several months and is delighted that you are part of this series. So without further ado, I'm going to turn this over to you, Elena, and you're going to give the talk in English, not in Portuguese, hopefully.
Eu posso falar um pouquinho.
Oh,
Bem-vindo a todos. Anyway, I lived in Belo Horizonte for a while.
I'd just like to remind everyone to mute their microphone, and if you want to ask questions,
I Maddie, you dropped off for a second. Can everybody hear me?
Yes, we
Yes,
can hear you.
yes.
Oh, we can
Okay.
hear you.
Okay.
I'm going dark while you talk.
Oh, no, that's fine. I think you muted just before you finished your sentence, and I was afraid that we had lost connection
well.
for a second.
Okay.
Anyway, thank you so much for having me. I am very glad to speak with you all. As Maddie said, I'm the Director of Research at a nonprofit Energy Science and Policy Research Institute based out of Oakland, California. And we do research on health and environmental impacts of energy resources and on clean energy transitions. And we try to think about how to get science into energy policy. My personal background, my PhD, was largely on batteries. I'm not going to focus on that today, but if anyone wants to stick around afterwards, that is one of my, personal interests. So what I think most of the talks that you've had so far in this seminar have focused on have largely been about the impacts of climate change in different sectors on food, for example. And instead, I am going to talk a little bit about some of the impacts of climate change on air quality and pollution, but I'm going to focus a little bit more heavily on some of the health benefits that can come from tackling climate change, specifically how reducing carbon emissions can reduce some of the air pollution and some of the emissions that are associated with our existing fossil fuel infrastructure. So I am going to attempt to share my slides. Let me know if this is working out all right. And here we go. Are we good?
We can see it.
Excellent. So I'm breaking this down into sort of three different components. The first is thinking about the impacts of our existing energy use on air quality and on climate. The second is I'm going to I'm an engineer. I'm going to go over strategies to actually decarbonize our energy systems. How do we transition away from all of these different technologies that are driving climate change and causing air pollution in our communities and across our countries? And then go through some strategies to sort of prioritize and achieve air quality benefits through these climate mitigation strategies. So first big question, what are the air and climate impacts of our current fossil fuel-based energy system? Where are we today? Sorry for everybody in Brazil, but most of this is going to largely focus on the United States. That's where I currently have most of my data aggregated. This is a plot. This is called a Sankey diagram of all of the energy use across the United States. On the left side, we have all of the sort of primary resources. So you can see solar and nuclear power and hydropower and wind are feeding into the system. Renewables are unfortunately not that large. This is recent data. This is 2019. And we get a large amount of contributions from natural gas, from coal, petroleum, and even biomass. Some of this goes directly into our homes and we burn it there for different end uses. Some of this goes through the power sector and we generate electricity and then we use it in different places. And then we often think about addressing energy use through the different end sectors. So these are residential and commercial buildings, industrial sector, and transportation. What we also see here is that on the far right is rejected energy and then energy services. Rejected energy, honestly, is like all of the inefficiencies in the system. Our energy system isn't that efficient right now. And there are many losses in there that we can try to tackle to reduce our sort of energy use overall. So this is the big picture. Our energy use across the United States is heavily dependent on fossil fuels, although again, that it's starting to shift. And these fossil fuels are one of the major drivers of greenhouse gas emissions in the United States. This is a plot of each of those individual sectors. This is from the EPA. And their contribution to US greenhouse gas emissions in 2018. Fossil fuel combustion, according to the Environmental Protection Agency, is responsible for about 75% of greenhouse gas emissions. And this is across, transportation sector, the power sector, industrial sector, and then, burning for gas stoves and heating and other things throughout our buildings. Another 10% or so comes from agriculture. I am not going to heavily address that sector here. There are also a number of non-combustion related emissions like methane leakage from oil and gas production throughout the natural gas distribution infrastructure across the United States that are associated with our energy use, but are not specifically combustion related. The EPA, we know, and tends to massively underestimate methane leakage. So this actually may be a bit of an underrepresentation of some of the fossil fuel impacts or the greenhouse gas impacts of our fossil fuel use. So where is this actually coming from? This is a plot of just greenhouse gas emission, like CO2 emissions. On the left side is the energy consumption from each individual fuel in 2019. So we have a large chunk from natural gas, from oil. Coal is actually rapidly declining, which is promising. And then on the right side are the CO2 emissions associated with each of those individual fuels. What you'll notice, for example, is that coal, while one of the smaller contributors to our energy use, is a relatively large proportional contributor to our greenhouse gas emissions, and frankly, a very large contributor to a lot of our air pollution. And so we may see different benefits if we replace different fossil resources in terms of the greenhouse gas and the air pollution impacts of displacing those fuels. What's interesting here, and this actually is a sort of larger political discussion about how the United States thinks about its greenhouse gases. I pulled this from the Energy Information Administration. This doesn't take into account methane leakage, which again is sort of systematically underestimated throughout our sort of national inventories. If you look at a 20-year time span, current estimates would say that natural gas consumption actually results in a greenhouse gas impact that is more than 90% higher than the direct CO2 emissions. And so those near-term climate impacts of our natural gas use are probably significantly higher than that proportion showed here on the right side. These fossil fuels not only produce, carbon dioxide and methane, both throughout the production and then combustion, but also are associated with numerous criteria and hazardous air pollutants that can cause a whole host of health impacts. I've listed a few of these here. One of the sort of primary ones is particulate matter, PM2.5, which is associated with, acute cardiovascular events, premature mortality, respiratory disease, such as, asthma-related hospital visits among children. We also, actually ozone is listed here. This is not a primary pollutant. This is a secondary pollutant. I should probably take a step back. Many of the fossil fuels both release primary pollutants that come out of your fossil fuel power stacks and out of your tailpipes on your vehicles. And these can cause direct health impacts, but many of them also react in the atmosphere to cause secondary pollution. And so, for example, the emission of nitrogen oxides can cause direct health impacts, but it also reacts to form additional secondary particulate matter and ozone, which will have additional health impacts both in that regional area and over an entire broad region. The result of this is that many of the health impacts of these pollutants are not, you end up having relatively high health impacts close to the source, wherever those emissions are, relatively high per capita, and downwind from wherever that source is. But you also can get secondary formation of pollutants that are very, very far downwind and can even affect populations hundreds of miles away from that pollutant source. Additional fossil fuel pollutants again include sulfur oxides, which can also react to form particulate matter, hazardous air pollutants, and of course, all of the greenhouse gases we discussed, which can have direct and indirect, largely indirect health impacts as well. But, sorry, next slide. So this plot is actually an even more complicated but kind of fascinating figure, which shows all of the actual deaths that are associated with particulate matter emissions across the United States. Current estimates suggest that these reach about 100,000 people per year. And about half of these are from fossil fuel combustion. On the left side here, we can see that those emissions are coming from, industrial and commercial sectors, transportation sectors, food and agriculture, and some from residential and electricity. And that these contribute, as we said earlier, to primary PM2.5. Those are up on the top right of the screen. But they also contribute to premature mortality associated with the exposure to secondary particulate matter, which results from the emissions of things like nitrogen oxides and sulfur oxides. What is also worth noting is not only the total impacts that are associated with these pollution sources, but also that we tend to have sort of disparities in those pollution impacts. Across the United States, particulate matter actually has decreased pretty significantly over the last few decades. But there are disparities in which neighborhoods are heavily polluted and which are not. And some fascinating research that came out earlier this year showed that some of the most heavily polluted neighborhoods, if you're one of the most heavily polluted neighborhoods in 1981, you're probably still in one of the most heavily polluted neighborhoods in 2016. So this plot on the bottom, you can see the sort of percentile rank of every census tract in the United States and its particulate matter concentrations. And up here on the left side is the rank of each of those individual census tracts and its particulate matter concentration in 2016. And again, the most heavily polluted communities in 1981 are the same as the most heavily polluted ones in 2016. So those disparities keep on getting propagated. There's almost too much to go into in terms of the pollution associated with the full life cycle of fossil fuels, but I'm going to try to touch on a few of those here, starting with each of our sort of like primary fossil fuels. So when we look at oil, there's adverse health outcomes such as low weight birth weights and with living near oil wells. Oil wells and oil production is associated with the production of things like volatile organic compounds and hazardous air pollutants like benzene. And these can provide health hazards for populations who live near oil and gas production. And then of course we see significant health impacts associated with the combustion of oil, particularly throughout the transportation sector and on our major roadways. The picture on the right here, actually, I took when I was driving down California to visit a friend at some point. This is just off the side of the road, sort of on the way down to Santa Barbara. Coal, we of course have environmental impacts associated with mining, but very notably, coal is the largest source of power sector health impacts from combustion of coal in large power plants, particularly particulate matter, nitrogen oxides, and sulfur oxides. And then you also have environmental impacts associated with the emissions of things like mercury. Coal has some additional impacts that can travel along other vectors in addition to air. I mean, so do oil and natural gas, of course, such as a lot of the coal ash, which is left over after you combust coal, is kept in what are called coal ash impoundments, these ponds next to the power plants. And sometimes these are unlined pits. Some of them are not kept up very well. Some of them get flooded, and this can leach into the groundwater and cause very high concentrations of things like heavy metals. And then natural gas is associated, like oil, with adverse health outcomes near gas production and processing. There are hazards associated with things like underground gas storage and gas transmission. Here in California, we had a massive leak of methane from an underground gas storage facility called Aliso Canyon, sort of outside of Los Angeles. And that released a bunch of mercaptans, which are put into the natural gas, as well as an odorant, so people can recognize that natural gas is leaking. Tons of people had to evacuate. And we've had explosions, which have killed people. And so there's a number, there's many hazards associated with natural gas use in that way. We have air pollution from natural gas combustion at power plants. And then natural gas is largely used in homes as well. And this is where we see increased risk to indoor air quality. Using natural gas for, let's say, cooking can produce nitrogen oxides, often exceeding air quality standards. It can produce formaldehyde. This can also particularly have impacts in households that tend to be lower income households, for example, that don't have proper ventilation. So sort of what I noted, a couple slides ago is that you have a certain number of areas that have high persistent levels of pollution. This is true sort of across the United States. So we see a pretty inequitable distribution in the impacts of pollution. And often these high cumulative pollution burdens occur in communities that also have high socioeconomic burdens and health burdens, which tend to make them more vulnerable to pollution. So for example, you tend to see more adverse health outcomes that are associated with low-income households that tend to have sort of higher socioeconomic vulnerabilities, such as lack of educational attainment, populations of color, and so forth, even when exposed to the very same pollutants. And then what we see is that many of these communities have disproportionate share of that pollution from our existing fossil fuel infrastructure. So in order to tackle some of these problems, here in California, we, and by we, I mean the California EPA, created a tool called CalEnviro BioScreen, which helps try to identify what we term disadvantaged communities. These are communities that have high socioeconomic and health burdens and high cumulative pollution burdens. So the tool integrates a whole bunch of indicators, such as income levels and linguistic isolation, combined with things like asthma rates, and other sort of health indicators that might make populations vulnerable to pollution, combined with pollution sources such as Superfund sites and particulate matter and pesticides and things like that. And this has been used to identify communities that are both vulnerable and have high cumulative pollution burdens for targeted investments in clean energy and in pollution reduction. So we have a lot of carve-outs and specified funds for, let's say, solar that targets those communities, or initiatives to try to reduce power plants or deploy electric vehicles and things like that to reduce pollution in these like historically overburdened communities. And so this sort of approach to thinking about how we can reduce pollution, particularly for those most vulnerable populations, I will sort of come back to in some of the following slides. I do want to take a quick aside here to note that I'm talking about all of the problems with fossil fuels, and I'm about to jump into the solutions, what we do instead. And I do want to note that many of the renewable energy resources and energy storage do have environmental concerns associated with them. These range from things like mining. For example, the cobalt that's used in batteries is often mined by children in the Congo in awful conditions. Solar and wind, of course, have land use considerations. Are these being put in ecologically vulnerable places? Using biomass has huge potential land use impacts and can also be associated with criteria pollutant emissions when combusted. And there's definitely a lack of sort of planning around end of life and what we do with things like solar panels and batteries when we get to the end. So most of these are not related to air quality specifically, but I think that they're sort of important to note that even as we move forward and try to mitigate all of these sources of fossil fuel pollution, that what we're replacing them with are imperfect. And we need to make sure that we don't continue to sort of propagate some of those pollution impacts of these as well. So that's sort of the lay of the land of the existing fossil fuel infrastructure and where all of our where greenhouse gases and our energy related pollution is coming from. So the next big question is, how do we get rid of it? What do we do? So how do we transform our energy system to basically enable 100% or close to 100% renewable energy across all sectors? So this is a figure from the, I think, former now head of the IPCC, the Intergovernmental Panel on Climate Change, in a commentary she wrote a couple of years ago, and unfortunately I don't know if we're on pace. But this is basically what we have to do to climate, to greenhouse gas emissions in the coming years if we want to have a chance of keeping our emissions below 1.5 to 2 degrees Celsius. I mean, our temperature below 1.5 to 2 degrees Celsius of warming. Basically, what this is pointing out is that the faster that we rapidly decrease emissions, the longer that we have to actually fully eliminate greenhouse gas emissions across our entire economy. What is notable is even in the sort of most rapid scenario where we turned around emissions in 2016, which I don't really think we did, we still have to very, very rapidly cut greenhouse gases across our entire economy. So the question is, how do we do that? I like to think about how we achieve 100% renewables or close to 100% renewables, a clean energy economy in like under three basic strategies. The first one is to increase energy efficiency. And so that just means making more efficient, cars, appliances, buildings, using less energy overall will make this entire problem a lot easier. The second component is to electrify everything. And so what that means is that we have to take our vehicles, we have to take our gas stoves, we have to take every end user that currently burns fossil fuels and electrify it. On a plus note, electrifying things actually makes them more efficient. So electric cars are more efficient than gasoline powered cars. And then the third step, and these sort of happen all simultaneously, is we have to decarbonize our electric grid. And so that means that we have to retire all our fossil fuel power plants, rapidly expand solar and wind, and then we not only run all of our existing, electric appliances, but also everything that currently burns fossil fuels off of that clean electricity. That's actually going to mean that we're probably going to have to roughly double the amount of electricity that we currently generate today in order to supply all of those different end users with sufficient energy. In the coming year, I forgot which slide was here. So, one of the big things that always comes up is thinking about how do we deal with the variability that's introduced by things like solar and wind power. As we know, the sun sets and the wind doesn't always blow. So there's sort of three basic strategies to deal with that variability and intermittency of the electric grid going forward. Historically, we have thought about our power sector and our energy sector in a way where we generate electricity And then that electricity, we sort of ramp up and down power plants in order to meet supply. What we're going to have to do going forward is we have to balance that back and forth. Maybe what that means is we shift more of our energy use to when the sun is shining. And so you have to create some kind of grid flexibility. We shift around our electric loads to match that solar and wind generation. The second strategy is we can store energy. We can store it in batteries. We can store it in many other ways. Right now, hands down, the most common way of storing energy on the grid is something called pumped hydro. We literally just pump water up a hill, leave it in a reservoir, and run it back down again when we need it. And the sort of third strategy is resource diversity, integrating renewables over a really broad area. And that tends to smooth out all of the things like a cloud passing over a solar panel and so forth. And so there's sort of like, I would say, I also tend to break down how I think about this into 3 sort of decadal steps in terms of how we get to 2050 to transform our entire energy sector. In the near term, in the next sort of 5 to 10 years, we have all the technologies we need. Everything is ready to go. We just need to very, very quickly expand solar, expand wind, make our buildings and our appliances and everything else more efficient, and stop building fossil fuel infrastructure so that we don't get locked in. In the midterm, we need to start now sort of doing large scale pilots of technologies that we know how to build, but maybe aren't quite as commercially viable, so that those are ready to hit the ground running in 2030 or so. And then in the long term, there's still a couple of technology, I'd say, gaps where we're not quite sure what it's going to look like. Getting from 90 to 100% renewables is pretty hard. And we might need longer duration energy storage, for example. We need better strategies for dealing with end of life of materials. I have no idea what we're going to make roads out of. They're currently made out of asphalt, which is, derived from oil products. So ongoing research now will mean that hopefully those things will be ready to go by the time we're trying to cut those last emissions from the grid in 2040 or so. So those are the sort of background steps of how we decarbonize. And then a lot of what I work on and think about is how can we use those decarbonization strategies to facilitate pollution reduction. So I'm going to go through this sort of like on a sectoral basis, one by one. And I think sort of start out with an overarching framing, which is just reducing greenhouse gas emissions doesn't necessarily achieve the greatest health benefits. There have been a number of studies that have shown that different kinds of greenhouse gas decarbonization strategies, basically, will achieve greater health benefits than other ones. That's what this figure is on the right. This is comparing a couple of different power sector related decarbonization scenarios. And some of them reduce basically more co-pollutants for every unit of greenhouse gas emitted than others. And some of them reduce more pollutants next to people than others. And so if we just focus on carbon emissions, we're not necessarily going to see the greatest health benefits from this, at least in the near term. Once we eliminate everything, it's probably fine. But in the coming decades, we're going to see much greater health benefits if we also think about air pollution in the process. And the other thing, and this is what I'll sort of touch on as we go through, is, as I said, many communities tend to have a cumulative burden of a lot of pollution. And those communities are also the ones that are probably going to lack access to things like solar panels and electric vehicles and everything else. So if we want to reduce those disparities in pollution, we have to do so actively, rather than just thinking about greenhouse gas mitigation as a climate-only problem. So to decarbonize our power sector, the sort of basic technology levers are: we add solar power, we add wind, we add other renewables like geothermal as we can. We can replace some of our most polluting power plants with other technologies, like we're starting to replace some power plants with batteries. And we can reduce our overall energy demand with energy efficiency, as we mentioned earlier. From a health standpoint, that's not necessarily quite sufficient. As we said, there are a number of different studies that have specifically found that the time that you introduce sort of clean energy technologies and the place that you add them also has a distinct impact. So for example, if you have a battery that is, let's say, charged by some excess solar power in the middle of the day, and that battery is discharged to the grid, it might displace some hydropower or a relatively efficient natural gas combined cycle plant, or it might displace a coal plant, which is going to have significantly higher air pollutant emissions associated with it. And so if you just go by default, it may or may not have those health benefits, but there are specific strategies that you can put into place that can actually prioritize which technologies you adopt when you dispatch those technologies, so you can target and displace those most polluting sources on the grid. The other thing that we think about a bit is where those are located. As I said, the air pollutant emissions don't just impact the immediate community. They certainly can cause air health impacts, tens and even hundreds of miles away from the source. But you do tend to see the highest per capita impacts next to those pollutants, next to those sources. And so what we frequently do is we look at who is actually living nearby. This is some research that we did here in California. On the left is a map of all of the power plants overlaid with that cumulative environmental justice screening tool, CalEnviroscreen, that I showed a few slides back. And on the right side is a plot of all of our power plants by the percentile of that CalEnviroscreen tool. And so if you're over on the right side of that plot, that means that you are in a community that has higher combined sort of socioeconomic and pollution burdens. And what we can see, and this is true in a lot of places, is a hugely disproportionate number of power plants in California are located in what we consider disadvantaged communities. We've looked specifically at something called peaker power plants, which come on about 5% of the time to meet peak demand in usually on hot summer days when air quality is bad and everyone turns on their air conditioning. And those peaker power plants, half of them are located in the 25% most disadvantaged communities in California. Some of them operate up to 2/3 of the time that they're operating on days that are exceeding our federal ozone standards. And so this opens up an opportunity. We're rapidly transforming our grid. We're deploying solar and storage. And so what we do here is we have an opportunity to actually adopt things like giant batteries to replace some of those most polluting plants in some of your most vulnerable communities and operate them on those days that we already have poor air quality and preferentially use cleaner technologies. And so those are some of the strategies that we're starting to think about as we move forward. This is the transportation sector. The sort of technology levers for transitioning the transportation sector include electrification of passenger vehicles and also, very importantly, of trucks. We've been doing some work across New Mexico and Nevada and Colorado, and I would say roughly half of the pollutant emissions come from medium and heavy duty trucks. So just adopting electric vehicles across the residential sector isn't going to be enough. That's still where we see a lot of our on-road pollutant emissions coming from. We also can take alternative strategies such as trying to expand public transit, trying to work on urban planning so that we have more walkable communities. From a health standpoint, we also found that if you're in the next 10 years or so, we expect residential vehicles to get replaced and electrified more rapidly than trucks. And what that does is it's probably going to leave high cumulative burdens in certain areas. And so we may need additional strategies to try to reduce some of those pollutant emissions, again, from things like trucks. And those can be things just like truck efficiency standards to trying to reduce things like truck idling and so forth. So we might need a wedded set of greenhouse gas and criteria pollutant strategies. And of course, as we said, you have those disproportionate pollution impacts. So this is some data that we are about to publish in Colorado. And this is the density of on-road vehicle emissions from particulate matter. By sort of, we broke down census tracts into quintiles by their emission density of particulate matter. That emission density is shown on the bottom in the orange. What you'll see is that you have, about 20% of your census tracts really high particulate matter emissions. And what we see on the top left is that those tend to be slightly more in low-income neighborhoods, and on the top right, that those high emissions across Colorado tend to be disproportionately in communities of color. And this tends to be true in many places that we look across the United States. And so again, we may need to think about specific strategies to reduce some of those pollution impacts. From an industrial standpoint, that sort of technology approaches for many industrial activities is to replace fossil fuels with hydrogen or to electrify end use. And in some areas, a lot of industry emissions are associated actually with oil and gas production in and of itself. So what we see here on the right is on actually October 30th, just a couple of weeks ago, New Mexico just redid its greenhouse gas inventory and has quadrupled their emissions associated with oil and gas production. More than half of those emissions of greenhouse gases, largely from, I think about a third of them maybe from methane, are associated with production. So you can do all of the decarbonization that you want in other sectors. You have to also think about ramping down your fossil fuel production at the same time. That being said, we still expect people to use oil and gas on an ongoing basis for some number of decades, and a lot of industrial pollution emissions aren't actually related to fossil fuel use. You can have other emissions related to mining and other things like that. So we may have to put into place some health protections, such as setbacks from wells, setbacks from refineries. We need more air pollution monitoring to even know what kind of pollutants are coming out and where there might be pollution hotspots. And things like emission controls for methane and oil and gas production can actually also help reduce the emission of things like volatile organic compounds as well. And again, same theme as before, maybe particularly valuable to sort of target electrification in those communities with high cumulative environmental burdens. In buildings, the technology approach for decarbonization tackles efficiency measures, helps reduce your overall energy use. You can use rooftop solar, electrify all of your appliances, as we said before, to try to get fossil fuels out of the house. This is important from a health standpoint. As we said, combusting natural gas, for example, in your home is associated with indoor air pollution, sometimes quite high, particularly when you're cooking. We're doing some measurements right now actually to try to see what else is coming out of the natural gas. Some of my colleagues are measuring natural gas in homes. As one of them always says, the pipeline ends here, like the pipeline from production ends in your kitchen. And they're looking for things that are mixed in with that natural gas, like benzene and other health harming pollutants that might be leaking out. And so as we decarbonize our buildings and introduce efficiency measures, it is also important to take into account things like proper ventilation. And then from a sort of broader health standpoint, actually thinking about things like efficient cooling, particularly as we're going to see increasing heat waves and risks of heat stroke in coming years. That some of these clean energy measures can actually provide climate resilience. And then of course, and we can show you more data on this later, low-income households and populations of color tend to lag behind in access to many of these technologies. And so we may need, funding and upfront financing for them to have access. And there may be particular benefits for vulnerable populations to have access to clean energy technologies like solar and storage, and efficiency and ventilation. So what that looked like in some of the work we're doing in Colorado is we integrated here extreme heat and places that we expect to see extreme heat in the sort of like 2030 to 2050 timeframe. So this is where people might be at particular risk for heat strokes. We plotted wildfire risk. This is where you, again, might have smoke and air quality impacts. And of course, wildfires increasing across Colorado and all of the Western United States as we get more drought, as things heat up, and as the pine bark beetles kill all of our forests. And then we also plotted the energy cost burden, the percentage of people's household bills that they actually spend on their utility bills, on electricity and on gas. And so those are households that might struggle to pay for electricity, but if they don't, then they might be more vulnerable to things like heat stroke. And so when we put screens like this, we can say like, all right, some of these communities where we see this overlay of like fire risk, where we see high energy burdens, where we see high, extreme heat coming up, this might be where it would be particularly valuable to incorporate things like solar and storage for resilience, to reduce bills, to provide backup power, to ensure people have access to things like clean air and cool air in a changing climate. So I wanted to touch on a few other issues related to climate, air, and health. Again, I didn't go deeply into this, but there are also very direct air quality impacts of climate change. I've been talking about some of the potential health benefits, but these include directly the conditions that produce ozone, tend to be hot summer days. Those are going to increase in the coming years. I think estimates suggest that maybe we've already seen this something like a 2% increase in like ozone related deaths associated with climate so far. That's supposed to continue. And then we have indirect effects associated with air quality effects associated with climate change, so things like wildfires and might be associated with land use changes, changing precipitation patterns, desertification, and dust. And so all of those changing, like, precipitation can help wash dust and things like that out of the air. Those patterns are going to be changing. So we might be see some changing concentration of pollution depending on changing weather patterns and things like that. This, just for funsies, of course, is a picture of, I was backpacking in, as we were talking about at the beginning, in the middle of the mountains in September when one of the big fires came up. And so this is what California starts to look like all the time now from a wildfire impact standpoint. The sky here was blue at 7, and this photo I took at 9 o'clock, and we were completely covered. I wanted to talk briefly about what's happening during COVID. During the first few days, or first few months, I guess, when a lot of places were under lockdown, global CO2 emissions dropped actually quite a bit, which seemed promising. But unfortunately, it seems like some of those emissions are rebounding, and they didn't drop as much as we had hoped, or, if we go back to those earlier slides, like this is almost that curve that we needed to meet our climate targets to begin with. So it's a start. Another co-benefit is actually we have a bunch of air quality monitors just north of where I work in Richmond, California. And you can see the emissions. This is sort of on the left side before and after shelter in place. For a couple of weeks before and a couple of weeks after, and the particulate matter concentrations dropped reasonably. probably due to a reduction in traffic and maybe some industrial operations in that area. So, this is very, very clear impact of, reducing fossil fuel use will reduce your air pollutant emissions, it reduces your greenhouse gas emissions. But, the real question now is like, what can we keep on doing this moving forward? So we've had this crazy set of impacts associated with the pandemic, of course, but they're starting to put us on the right trends from an air quality and greenhouse gas standpoint. Is that something that we can maintain? Maybe there's an opportunity for, COVID-based economic recovery to support, to be based on investments in clean energy resources. What I was trying to emphasize, hopefully these can also be focused particularly in areas that have high, environmental burdens that are historically underserved, so that some of those disparities in pollution can be mitigated as well, and that we can sort of increase resilience for those vulnerable communities as climate impacts continue to grow. And I will leave it there, and we can open up to some questions. I'm going to stop share so I can see comments.
Good. No, thank you very much for really a very enlightening intellectual overview. Obviously, in 50 minutes, it's almost impossible to do justice to this complex topic. We didn't even talk about the economics of trying to do all that. But I'd like to, but I'd like to turn your attention to the chat because there are a couple of questions. One asks, can you speak to the growing concern large-scale hydropower projects are and will have adverse impacts on disadvantaged people?
Yeah, hydro is sort of a fascinating one. Hydropower can come into play both from hydropower generation and then this pumped hydro storage, which I spoke about earlier. In the United States, a lot of new hydropower it's not happening. No one's building new hydropower here. A lot of the impacts of growing hydropower have been, I would say, like in China, and I'm going to ask everyone in the audience, maybe in Brazil, and those have displaced large populations. Many of those actually, when they flood areas, are associated with increased methane emissions from anaerobic decomposition of plants when they get flooded. And so there are definitely significant adverse environmental and population impacts associated with expanding hydropower. I think that there are a couple of opportunities to try to increase hydropower in a more sustainable way. Those include things like run-of-river hydropower. These don't require dams. They just take advantage of the existing sort of speed of flow to run turbines. And there's ways that you can do, people are thinking about doing pumped hydropower, as I said, in closed loop systems, even in things like old abandoned mine shafts, where you don't have any existing populations or anything like that. So what we might think about from like a hydropower standpoint is expanding some of those smaller systems, or upgrading some of our existing hydropower facilities that are often very old and not as flexible. But the new ones, do have a significant number of concerns across the board.
Thank you. Also, I mean, as we all talk about renewable energies, to try and transition to that, there are some negative effects of that we do have to address. For example, with the wind turbines, there's noise. And too has to be studied carefully. So we have to be very careful if we're going to make this jump. Well, it's not going to be a jump. If we're going to take these baby steps to get to where we need to be, we have to make sure that we're not adding more harm to the vulnerable populations who might be living near these wind turbines, for example. Can you speak on that? With compressor stations, that we, I mean, those are terrible to live near.
For all of these, I think that it's important to have certain kinds of setbacks from communities, both like human populations and animal populations. Certainly, wind turbines are associated, you want to keep those out of like migratory paths of birds and so forth. And so there is a balance here, which is that everything will have some kind of impact. And we'll see in some areas that nobody wants anything built, and you have to build something somewhere. And so the question is trying to like mitigate those as much as possible and make sure you take the whole lifespan into account, both from like the production of materials to what you do at end of life, as well as what happens sort of continuously, and make sure that the populations who are living near any of those facilities have a voice and also can potentially benefit maybe economically or something else from that expansion of technologies. I think MJ here commented that they're trying to expand hydropower in Canada. That sounds about right, actually, for supplying the Northeast. New York, for example, actually relies significantly right now on hydropower imports to meet some of its energy generation. And I think they're trying to use that to meet some of their renewable energy targets, which are pretty aggressive. And so actually what you see here is a little bit of an interesting political trade-off, which is a lot of New Yorkers have been really anti-building out solar and wind in their state. It's been very hard to build those resources, and there's been a lot of pushback. And instead, if they are indeed trying to build out in Canada instead on tribal lands, it means that they're basically trying to export those environmental problems. And this is what we see, across the board, that nobody wants those impacts in their communities. They want somebody else to have those impacts instead. And unfortunately, that's true for renewables as well as, fossil fuel resources, industrial facilities, and everything else.
NIMBY has always been an issue, and hydro power from Quebec coming down to the Northeast has been, this is nothing new. There's nothing, that's about that. But I think we have to be a little bit more sensitive and a little bit more sensible about how we move forward. I just want to mention that we are now reaching the hour 6 o'clock, and I am very mindful that people have had a long day. So I will formally thank you, Dr. Krieger, for your talk. And for those who wish to stay on, please feel free to do so. Dr. Krieger said that she would be able to do this, to answer questions and have a conversation, for a few minutes after the hour. So for those that are signing off, let me just wish you all a very happy Thanksgiving. It's coming up next week here in the United States. And to also let you know that we will have our next session where we will look at climate change and vector-borne diseases on December 8th, which should be very enlightening, of course, but maybe even a little scary, conversation. Not that this was not scary when you start to look at it. So thank you all for joining us, and we will stay on for those that have some questions.
Also, feel free to email me. I have my emails, my last name at pscehealthyenergy.org. So yeah.
That's good. And that picture that you took of in California is very sad.
Yeah.
Because I assume that those mountains had a lot of trees before the fires.
I think that, so actually right up there, that didn't get burned down. That was just smoky.
Oh, sorry.
Yeah.
It looked kind of desolate. So.
It's kind of desolate. That's because you're at 11,000 feet.
Okay.
Yeah.
There we go.
No, but it actually, half the places I backpacked this spring have now been burned. It's really been pretty disturbing.
Yeah. I don't see many questions coming in, which means you either were so clear in your explanation or that you just numbed everybody.
Might have numbed everyone with a lot of information.
But I am personally quite happy that you did bring in issues of environmental justice, because as you know, I study that, the oil and gas drilling pipelines. And you're not going to see these in wealthy communities. They are always communities of low socioeconomic and minority communities. And that's not cool. That's not good.
No, you see it across
Amar
every
says this
sector.
was we cool. Okay, I agree. That was good.